everyone. Welcome to the next webinar in our Thought-Provoking Thursday series, Protecting Your Assets, Lubrication Best Practices for Gearboxes. Before we get started, I want to review a couple of quick housekeeping items. This webinar is being recorded. You will receive a link to the video within the next day, and it will also be posted to our website at dustcase.com. If anyone has any questions during the webinar, please type them in the question panel of your GoToWebinar screen. At the end of today's session, Jared will be answering some of your questions live on the air. If we do not get to your question, we'll be reaching out afterwards to provide you with the information you need. So thank you so much to everyone for attending. Today's speaker is Jared Pottinger. He has more than 20 years experience in the field of precision lubrication. Jared has served as the Director of Services for Dustcase Corporation for more than 10 years. He has trained thousands of maintenance professionals on the subject. He has authored dozens of articles and one book on precision lubrication. Jared holds a Bachelor of Science degree in Chemical Engineering from the University of South Alabama. Jared, thank you so much for being with us today.
Well, thank you, Olivia. Thank you for that introduction. And thank you to all of our participants for being here today. And this is Lubrication Best Practices for Gearboxes. So this is going to be a rather basic and simple, but very important topic, and one where a lot of people, although it is relatively simple, still make a lot of mistakes. So we're going to begin by talking about what some of those mistakes are. So precision lubrication or best practice lubrication is what we're trying to implement for all of our assets, but gearboxes are a very common one, and gearboxes, many of them, don't necessarily fall into the category of our most critical assets, so they're sometimes overlooked. So we're going to talk about all of the major aspects of precision lubrication for gearboxes. So first of all, precision lubrication or best practice lubrication is not about using better lubricants. So good lubricants don't necessarily equate to good lubrication. Usually that's not the case. I'm not saying that there isn't value in high performance lubricants or synthetic based products, but a lot of times the problems that we have with gearboxes are not related to the quality of the lubricant. There are other things that are more important or that are bigger contributors to the problems. And we're going to talk today about what those things are. Hey, likewise, lubricating your gearbox more frequently is certainly not precision lubrication. There's nothing precise about that, and it's not necessarily better. In fact, if we lubricate things more often than needed, a lot of times we simply, best we're going to waste time and waste resources. But in a lot of cases, we can actually cause harm by over lubricating things. Or, if we change oil twice as often as we need to, then we're really doubling the chance that we're going to do something wrong, such as fill to the wrong level, or, possibly contaminate the lubricant when we add it, or use the wrong lubricant. So there's no reason to lubricate things more frequently than needed, and in fact, there is reason not to. So precision lubrication or best practice lubrication really requires that we do quite a few things right, and that starts with lubricant specifications. We need to make sure that we're using the right oil, not necessarily the best one. We haven't gotten to lubricant performance yet, but we want to use the right one, the right viscosity grade and the right type of oil. Then everything else that we do is really going to be about managing the condition of that oil. So we need to manage the health of that oil, which is the way we describe the chemical condition of the oil. So if an oil is in good condition in terms of its oxidation levels or thermal degradation, additive concentration, if all of that stuff is in good shape, we say that that oil is healthy. Then we also want to manage contaminants. So contamination control is going to be a big part of this, and that includes storage and handling, lubricant application methods. And then finally, all of this is made, I won't say easy, but made easier with education. Okay, if we educate all of our maintenance professionals on the fundamentals of precision lubrication, then we have a much better chance that we're going to get good results. And then finally, doing lubrication the right way, or we might say the preferred way, is usually easier than doing it the traditional way. So, for example, changing oil with a filter cart. Okay, the reason we do that is so that we get clean oil into the machine. But as kind of a side bonus, it takes about half as much time in the average gearbox to change oil that way. Taking a good oil sample requires the installation of a sample valve. So we do that so that we get good oil samples, but as a bonus, it makes it a lot easier to take the sample. So there's time savings, there's an improvement to safety, environmental concerns, etc. So this is what we're going to talk about today with respect to lubrication for gearboxes. We're going to begin by talking about just why it is that gears wear out in the first place. That will really illustrate what we need to focus on to have effective lubrication. So then we'll talk about lubricant selection. That one's going to be really easy. Talk a little bit about PM development for oil changes, for inspections, contamination control or lubricant condition management, and then we'll wrap it up with a little bit on equipment modifications which are necessary to achieve those other things. So again, why gears wear out, lubricant selection, PM development, contamination control, and then again, finally, equipment modification. So for our first section, why gears wear out. According to MIT, 15% of lost usefulness. Now, what they call lost usefulness, I like to think of as lost service life. So 15% of lost service life is caused by machines just becoming obsolete. So sometimes we replace them with something newer and better. Another 15% of the time, machines fail because we break them. So accidents, either a mistake in installation or selection or maintenance mistakes. But the vast majority of the time, the vast majority of lost usefulness or lost service life in our machinery can be attributed to surface degradation, which is what I call wear. So really what MIT has told us here is something that we all already knew, which is that machines wear out. They're supposed to. That's the natural way that machines die. That's the natural way that we limit the service life of machines is by the rate of wear. So what kind of wear? Well, we have a couple of different categories. We have corrosive wear and we have mechanical wear. And mechanical wear, of course, is the biggest piece. So that's the one we really want to focus on. But both of these types of wear are lubrication issues. So one of the functions of a lubricant is to minimize wear. Another function is to reduce or prevent corrosion. So both of those are lubrication related. They are lubrication issues. But again, let's focus on the biggest piece. Let's focus on mechanical wear. So if you look at the different types of mechanical wear, this information on the screen comes to us from a study that was done by STLE and the National Research Council of Canada. And in this survey, they studied 3,722 wear-related failures in machines. And what they found was that in 66% of cases, the predominant wear mechanism was abrasion, 12% adhesion, 8% erosion, and 8% fatigue. Now, adhesion, leave the other three aside for a second, adhesion is a type of wear that takes place when we have boundary lubrication conditions. That means we have metal-to-metal contact, and we don't have the proper film strength. So we don't have the right type of additives, or we don't have the right type of lubricant in place. So adhesion is kind of an abnormal wear mechanism that is caused by usually improper selection of lubricants. The other three, abrasion, erosion, and fatigue, are largely caused by one thing, and that is lubricant contamination. So it makes sense that that is where we should be paying a lot of attention. So particle contamination causes three-body abrasion. It can cause particle-induced erosion, and it causes particle-induced contact fatigue. Water and air contamination also facilitate this particle-induced wear by reducing the film strength. Water and air also cause other forms of erosion, gaseous and vaporous cavitation. So my point is that the vast majority of machine wear is caused by contamination to the oil. The vast majority of lost machine life is due to wear. So if we can control the root cause, contamination, and we can, by the way, we can control the rate of wear in the machine. And this doesn't only apply to gearboxes, it applies to any lubricated machine. So In as much as we can control the quality of lubrication, contamination control, we can control the rate of wear in the machine, thereby maximizing, or we could say optimizing, the service life of the machine. So lubrication for gearboxes can be very challenging, and I mentioned, one of the main reasons for that already, and that is that sometimes these aren't seen as very critical assets. Most gearboxes don't have circulating lubrication systems on them. So if we had a circulating system, we'd probably have filters in place. We'd probably have, or potentially have, an oil cooler in place and a good sample valve to take good oil samples. But for a run-of-the-mill bath lubricated gearbox, we don't have any of these things. So the oil level, when we don't have a circulating system, is very critical. The proper oil level for a typical bath lubricated gear is to completely submerge the lowest tooth on the driven gear. So if you picture that, you can imagine that the difference between the perfect oil level and one that's too low is not very much. So having the right oil level is very critical, and we can't just fill it higher because that causes a lot of problems too. That causes heat, it causes aeration in the oil, which is very damaging. So the oil level is very critical, and it can be challenging to maintain. There are startup issues with these, and that's not really something that we can do anything about, but it is an issue with bath lubricated components. We actually have to run the machine to distribute the oil, so that creates issues on startup and certainly for storage. It's difficult to control the temperature. You could say it's impossible to control the temperature. All we can really do to keep a gearbox cool is keep it clean, maybe put a fan on it or something. But in general, what we're going to have to do with respect to temperature is select our lubricant based on the operating temperature. So we're going to be reacting to that rather than controlling it. It's also very challenging to control contamination. We'll talk about that in a moment. There is a risk of inadequate lubrication due to temperature extremes, due to idle periods, startup, etc. And then there's the effects of wear debris. Because we don't have onboard filtration with these systems, we are going to have wear. Most gear sets do wear some, and that wear debris is going to build up in the oil. Now, that wear debris is going to become a harmful contaminant itself. It is also going to cause more wear. It's going to act just like other particles do. And it's also going to have an effect on the chemical stability of the oil, reducing the life of that oil. So at this point, I'd like to stop for about 30 seconds so that everybody can participate in the poll question that should be on your screen now. So please select the choice in the poll question that best fits your approach to this issue. Okay, well, that should be enough time for everyone to have finished their poll question. So we'll move ahead to our first topic, which is lubricant selection. So lubricant selection for gearboxes is normally really easy. We simply look in the book. So we find the OEM operating and maintenance manual, look for the lubricant specification, and there, we may actually need to, it may not tell us exactly what we need. We may need to actually kind of interpret that information in some cases. Maybe it just tells us a specific product, and maybe that product no longer exists. Maybe that product is made by a different manufacturer than the one we normally use for our lubricants. So sometimes we need to take that information and then translate it into a more generic form so that we can pick the right product from our inventory of lubricants. But anytime that we have a question on this and we don't feel comfortable doing that ourselves, you can always call your lubricant supplier or lubrication consultant and tell them what the equipment manufacturer is recommending, and then they can recommend the correct product from their product line that'll fit that. Now, from time to time, we may actually come across a gearbox that's very old, or it may be a custom gear set, or for whatever reason, we don't have that information from the equipment manufacturer. So there are standard methods for lubricant selection for gearing, and this is one of them. And this table that we see here is from the American Gear Manufacturers Association, and it helps us to select the right viscosity grade based on the speed of the application and the temperature. So when we select viscosity for any lubricated component, what we're really doing is specifying the amount of separation between interacting surfaces. So there are several things that affect film thickness. There is the speed with which surfaces interact, there's the load on the oil film, and then the viscosity. And of these three things, the one that we control is the viscosity. So we're gonna look at load, and many times we're not gonna really know the load, so we're usually gonna disregard that and just go with speed. So we're gonna look at the speed, and then if we know the operating temperature, that will allow us to select the correct viscosity grade for this application to give us the right operating viscosity. So the first thing to do is to calculate, in this case, the speed or velocity of the slowest gear in the system. Now, gears are a little different than many lubricated components in that we have components within the gearbox that are going at different speeds. So for our high-speed stuff, our viscosity is going to be quite high, but we want to make sure that we protect the low-speed components with enough viscosity. So that's why we're always going to look at the slowest gear in the system. So we calculate the pitch line velocity of that gear, which is basically just the circumference of the gear. So that's the diameter of the gear times pi times the output speed or rotational speed, and we convert that to meters per second. So just imagine that we have, in this case, approximately 10 meters per second. And then we have identified, or maybe have to estimate, that the highest likely operating temperature, again, we always want to go for the worst case scenario. So we look at the highest temperature, make sure we have enough viscosity. So in this case, we said it's going to be 65 degrees C. So that puts us squarely on an ISO 220. So now I failed to mention previously that this selection table is for non-worm gears. So really, when it comes to lubricant selection, we have two categories of gears. We have worm gears and everything else. So worm gears are going to be treated a little bit differently. We'll get to that in just a moment. So now that we have the right viscosity grade, in order to select the right lubricant, we need a lubricant type. So we're going to have to choose an anti-wear oil, an R&O oil, or an EP oil. So in this case, in the case of our AGMA lubrication standards, there's not a number here. There's not a formula. There's not a calculation. Okay, it's really a little bit subjective. So in this case, they're telling us if we have moderate to heavy shocks on our driven unit or the driving unit, that we should use an EP gear oil. If we have light or uniform loads on both of those, we could use an R&O oil. But here's the thing. It's very difficult to know. Like I said, there is no calculation, at least one that we could do reasonably, that would tell us EP or non-EP. So when in doubt, for all of our reducers, now this doesn't really apply to high-speed gears, but for all of our reducers, when in doubt, use an EP oil. There are multiple types of EP, but our standard EP oils are sulfur phosphorus oils. And there are some times that we don't want to use sulfur phosphorus additives in our lubricants, namely with yellow metals. So we're not talking about worm gears at the moment, but it deserves mention that sulfur phosphorus additives should not be used with worm gears, because sulfur phosphorus additives are corrosive. That's actually how they do their job. And they may be particularly corrosive to yellow metals. So we don't want to use them with worm gears, but we use them with just about everything else. So the other time that we don't want to use an EP agent is if we have an internal backstop in the gearbox. Now, these are not that common, but if you have an incline conveyor or an elevator that has an internal backstop in the gearbox, you need to be very careful with the lubricant selection. Consult the OEM documentation to make sure you're using the right type of oil, because an EP oil can actually cause a backstop to fail, potentially creating a big safety hazard. And then again, there are other types of EP additives. So if we have an asset that maybe has very heavy shock loading or very severe boundary conditions, there may be times when we want to use a solid EP like moly or borate or some other type of solid additive. So moving on to our next category of gears. So remember, we have non-worm gears and worm gears, but we're going to treat worm gears the same way with respect to viscosity selection. So if we have a certain temperature range and we have a pitch line velocity less than 2¼ meters per second, we're going to use a 680. And if it is above 2¼ meters per second, we're going to use a 460. Traditionally, we use compounded oils for worm gears. So this is what some people call cylinder oil. It has a special lubricity agent that is very good for the type of contact we see in worm gears. Again, we don't want to use sulfur phosphorus. Sulfur phosphorus, if there is boundary conditions, will likely be very corrosive to the yellow metal surfaces. If we have an extreme case for a worm gear, if we need improved lubrication or improved film strength, a lot of times people go with a polyglycol gear oil that is actually specifically designed for worm gears. So a lot of manufacturers make a high viscosity PAG oil specifically for worm gears, and it actually has really good lubricity and good wear preventing properties. And finally, if you have half a dozen gearboxes that use ISO 460 and you have 50 that use ISO 680, there's a good chance that you could use the 680 in all of them. So that's something to investigate. Now, we don't want to take a chance, but we want to verify that it's okay. But most machines can run on more than one lubricant. There's usually not one correct lubricant for a certain application. Usually they'll run on a range of viscosity grades, and in a lot of times they'll run on a range of viscosity types. So that's lubricant selection. That's the first piece of precision lubrication. Now we need to focus on how we manage the condition of that oil. And the big thing there is going to be contamination control. So when we control contamination, we need to follow a strategy. So we shouldn't just say, well, let's use filtration, or let's use good breathers, or let's upgrade our filters on our circulating systems. The right way to do it is to first identify how clean the oil should be. So of course we use particle count to measure that, or the ISO contamination code or ISO cleanliness code. So we need to set a target for particle count. We need to set a target for moisture limits. So those being our two primary contaminants that we're concerned with. Then the next thing we need to do is figure out how we can actually achieve those targets. Now we're going to talk about what most of those things are in just a moment, the various measures we can implement to achieve our cleanliness targets. And then finally, we need to be able to effectively measure if those actions were actually effective. So we need to be able to effectively measure the particle count and the moisture concentration. And that means good sampling and good oil analysis. So for step one in contamination control, we need to identify our target. So for gearboxes, this is a good one. 1916-13. It's a little ambitious, frankly. That's going to be hard to achieve unless you do things very well. So it will require lubrication best practices with a bath lubricated gearbox, one that doesn't have a filter built in. It's going to be challenging to hit 1916-13. And then a good moisture limit would be around 300 parts per million, which would probably be around the saturation point of the gear oil. So we typically want to be below the saturation point of the oil when it comes to our moisture limit, so that we don't have any emulsified water free in that system. So a lot of times actually achieving that target is going to cost. We're going to actually have to change the way we do some things. We may have to install upgraded components in order to achieve those. So how do we justify that? So we know that's how clean the oil should be, but why? What is that actually going to get for us? And this chart we see here is a very useful tool that I use commonly for cost benefit analyses. And what this shows me is what kind of change in service life that I should expect based on the particle count. And remember, this makes sense if we go all the way back to where we started, where we said that service life is determined by wear rate, and wear rate is really determined by oil cleanliness. So if we start out with a particle count in a gearbox, let's just say 23, 21, 18. That is in no way uncommon. That is probably a pretty typical particle count for a non-filtered gearbox. It's pretty dirty, but it's very common. So 23, 21, 18. Now we said our target particle count should be 19, 16, 13. Let's just because we have the numbers on the chart here. Let's just say 1917, 14. It's pretty close. So if I look at the chart here on the y-axis, I have relative component life. So this is just a relative number. It's not 20 days or weeks or months or years. We have, in this case, 45. So we have 45 units of service life at that particle count. And if we move to our desired particle count of 1916, 13, we're going to have about 90 units of service life. So the relative life of my gearbox with the desired particle count should be 90 to 45 versus the current particle count. So what that tells me is that if I do achieve my target particle count, I can get twice the life out of my gearbox. So that's one way to look at it. The other way to look at it is that my maintenance cost on that gearbox is going to be cut in half. So if that gearbox currently lasts, let's say 5 years, and it costs $10,000 to replace it, well, I'm currently spending $2,500 a year. If I change the particle count, it should go 10 years. So now I'm spending $1,250 a year. So I saved $1,250 a year simply by improving the particle count. And it really is that easy. May not be easy to do it. A lot of times it takes some effort to actually hit that particle count, but at least theoretically, it is that easy. And just to reiterate that particles are not the only contaminant that we're concerned with. This is a similar life extension table for water, or based on water contamination for bearings. So if you look at the orange line here, that's for element bearings. As you can see, if you go from 100 parts per million of water in the oil, where you have 100 units of bearing life, to about 1,000 parts per million, you've actually lost about 75% of your bearing life. So water, normally it does certainly cause corrosion, but that's not the primary way that water causes damage. The primary way that water causes damage is by reducing the film strength and thereby the film thickness, separating interacting surfaces in the machine. So the machine surfaces get closer together and more bad stuff happens. Now, I always like to include a case study in short courses like these. And it's hard to find good case studies on gearing because, for one thing, like in the example I just mentioned, we're talking about causing a machine to run 10 years instead of 5. So it takes a long time to collect that data. But I have one here that is for final drives on haul trucks. So at this particular, this is a copper mine, open pit mine. And they've done many things to improve lubrication, but one of the many case studies they did was using offline filtration for final drives on haul trucks. So in this case, every time they had the haul truck down for an oil change, every 500 hours, they would take a filter cart and filter each of the final drives. And they would do this, while they were doing other things. So they didn't take it out of service. It didn't take extra time or anything. The direct result of this was that their mean time between failure on final drives went from 9,000 hours to 13,000 hours. And their maintenance cost per operating hour per final drive went from $2.11 to $1.36 per hour. So that's about a 36% reduction. And at the same time, they increased the life of the oil from 2,000 hours to 6,000 hours. Differentials and final drives and a lot of geared applications have a lot of metal in them traditionally. So when that metal, in addition to causing more wear, also causes damage to the oil. It promotes oxidation. So when you remove that, the oil can last a lot longer. So that's why we see a 3 times improvement in oil life here. So what are the things that we can do to actually control contamination? Well, the good news here, if there was good news, the good news is that the vast majority of contamination in gearboxes comes from just 2 places. It comes from the new oil that we add to the sump, and it comes from the air that the case breathes. Those are 2 things that are pretty easy, at least theoretically, very easy to address. We can simply filter our new oil. Now, those of you that have tried this, you'll probably know that it's not really as easy as that. Just filtering new oil doesn't ensure that we get clean oil in the machine. That can take some effort. As far as the air that the sump breathes, there's several different headspace management techniques, but good quality breathers go a long way towards preventing particles and moisture from entering the sump. We can also use good application methods, and that's why I say there's more to it than just filtering new oil. We have to use good handling tools and good methods to get clean oil in the machine. We could upgrade seals. We need to utilize non-invasive inspection and sampling methods. This means using sight glasses as opposed to dipsticks and level plugs. It means using an installed sample valve instead of dropping a tube into the sump or sampling from the drain line. And it also means, using good flushing practices for new equipment. So we have startup, we have cleanliness on startup, and even managing our spares well. So that's unfortunately all we can do for a lot of our gearboxes. There's just not, we really can't justify, it's not practical in many cases to use filtration on gearboxes, but for others there are. And so if we have a gearbox that has a circulating system, we can look at upgrading the filters on that system. If it doesn't have filters, or if that's not enough, we can look at installing a kidney loop system on that. So for some large critical gearbox applications, that is a good option. For the others, our option really is portable filtration. Portable filtration is very effective. The question is, do we have enough time? Are we going to get enough back for doing that? So sometimes yes, sometimes no. And that's why I say we need to, with especially the lower criticality applications, we need to be vigilant about preventing contamination, because contamination removal, while very effective, costs a lot more money and takes a lot more effort. There's actually been studies that show that it costs about 10 times as much to remove contamination from oil as it does to keep it out. So that's always where we should focus. And one of the best ways to do that is with good headspace management. We can also upgrade seals in many applications. We certainly want to practice good storage and handling. So we definitely need to filter our new oil and use good quality transfer equipment, and also manage our parts well. So if we have spares sitting on the shelf, we need to think about contamination control and lubrication considerations with that stored equipment. But for the big topic here for gearboxes is headspace management. So again, I said most of the contamination that gets in our systems comes from new oil that we add to it. That accounts for a lot of particle contamination, but the vast majority of moisture contamination and a lot of the particle contamination comes through the breather. Most breathers, most OEM breathers, don't do a lot to stop particle contamination, and most of them do nothing to prevent moisture contamination other than keeping out, rain or water from washdown activities. Most of the water that gets into lubricated systems actually comes from condensation. Many manufacturing environments are very humid. So when humid air enters the sump, then the air cools down later, you get condensation inside. Anybody that has a boat with a fuel tank knows this. You always have water in the fuel tank on a boat because it breathes. You get humid air inside the tank, it cools down, you get condensation. That condensate falls into the fuel or into the oil, and you have water in the system. So the easy way to prevent this is to simply use a breather that stops the moisture. So a desiccant breather will pull moisture down to about 25% relative humidity. There are other ways we can do this. We can use a hybrid style breather that incorporates an expansion chamber. We could use just an expansion chamber that kind of traps the volume of air to be exchanged, prevents exchange with the outside air or the ambient environment. We could also purge the headspace with dry air or with nitrogen, or we could even use an oil mist system. If we have an oil mist system nearby, we could run that oil mist system into the headspace to prevent anything from coming in. So in a lot of cases, desiccant breathers are the preferred option. Now, when it comes to adding oil or for decontamination, for many of our gearboxes, again, most of them don't have circulating oil with filtration. So our best option is portable filtration. And what we see here is an example. And in this example, they were actually using the filter cart to change the oil. So the picture we see here is after the oil has already been changed. So as I said earlier, using a filter cart to do an oil change is the best way to transfer oil because it ensures that we get clean oil into the system. But it's also a really efficient way to transfer oil. So in this case, we're actually going to use the filter cart to remove the waste oil, and that's going to get the old oil out faster and more completely. So that's a good thing. we have bypass valves on the filter cart that can actually isolate the filters so we don't have to run the old oil through the filters if we don't want to. Then we reconfigure that system and we actually pump new oil through the filters into the case. And then in this case, they've actually taken that a step further. And once they've added the new oil, then they reconfigure so that they can circulate the oil in the case and make sure that it's clean. And I know that this works by looking at the patch tests that we have here. So if you look at the upper left-hand corner, that is a patch test. That's not really magnified, by the way, not much. That's a patch test for the new oil that came right out of a drum that was going to go into that gearbox. The one to the right of that, that's actually the waste oil that was being thrown away. And as you can see, it's much cleaner than the new oil was that was coming out of the drum. So even after a full term, even after a full oil change cycle, that oil was still much, much cleaner than the new oil. And then on the bottom here, we see the oil after it was filtered for 180 minutes, which may be a little extreme. We might not actually need to filter it that long, but that's certainly a good practice. And this is a microscopic examination of those patches. So here we see the unfiltered new oil. And as you can see, we have some very large particles in there and a whole bunch of small ones, most of which are very damaging to our gears. And then in the next picture, we see a microscopic examination of the filtered oil. Now, when you consider that those particles that we see on those slides, that is the #1 contributor to machine wear and really the ultimate determiner of the service life of that asset, it certainly makes sense that we could get twice or even 3 times the life out of a gearbox by going from the previous to this oil. And at this point, we'll stop for another poll question. You should see it on your screen there, and we'll wait about 30 seconds for everyone to complete that poll question, and then we'll move on. Okay, well, that should be enough time. So now that we've talked about how to select the right oil for a gearbox, it's easy. How to manage the condition of that oil, how to prevent contamination and how to remove contamination, not necessarily as easy. Now we need to talk about another aspect of this, something that enables all of those things, which is modifications. So usually when it comes to implementing precision lubrication, this is really the physical work that has to be done. This is in terms of changes to the equipment, changes to the program. If we want to use filter carts to change our oil instead of using traditional methods, then that is going to require that we have quick connect fittings on our reservoirs so that we can actually use the filter cart. Otherwise, the filter cart is pretty much worthless. So this is a huge issue. It's a huge part of implementing precision lubrication. If we want to take an oil sample, especially on a gearbox, we need to install a proper oil sample valve so that we can get good samples and so we can get them very efficiently. If we want to prevent moisture and particles from entering the headspace, then we need to modify the sump with a breather or with an air purge or something else. So there are basically 3 different reasons that we modify equipment. We modify equipment to enable certain lubrication activities that we may not be able to do now, such as adding oil with a quick connect hand pump top-up container or something. So we need to do modifications for lubricant application. We need to do modifications for inspection. So if we want to check the oil level regularly, we need a sight glass. Level plugs are really inefficient and a good way to contaminate the sump. Dipsticks are also a good way to contaminate the oil. And then finally, we need modifications for contamination control. So we need modifications for lubricant application, for contamination control, and for inspections. And this process of modifying equipment can actually take many years. And I would say on average, if you really went at it, it would probably take about 3 years to modify all of the assets in your plant. Not because it's such a big job, not because there's so much work to do, but because it requires access to the equipment, it requires, in most cases, or at least in many cases, it requires that the asset is down. So if we're going to add a sight glass or a sample valve or something that's below the oil level, we've got to shut the machine down to do that. So the right time to do it is normally during an oil change. If it's something that's above the oil level, like installing a breather or installing a quick connect so that we can add oil to the sump, that's something we can do right away. But the first and most important step in this process is to identify the preferred configuration. So you don't necessarily have to do a modification plan for every single asset in the plant. You can actually create a few templates that make this entire process pretty easy. So, for all of your gearboxes, you may need 4 or 5, maybe 6 different templates that you can apply to all of them, depending upon what type of modifications you want to do and what type of gearbox it is. And a lot of times what type of gearbox it is really going to affect where we install things. So a lot of times, different gearboxes will have ports available in different locations. So again, the crucial first step in this process is to identify the desired result, identify the preferred configuration, and then create a parts list with any specialty parts, that have to be ordered in order to do that modification. And then it can be scheduled in an efficient way when that equipment is available. And like I said, there's not a lot of different configurations that we need for gearboxes. So it depends on, in this case, we have a gearbox that only has 2 ports. So in this case, we have combination fittings that allow us to put all of our accessories into just a couple ports. So we have at the top, we have a breather and we have a quick connect fitting. On the drain port, we have a quick connect fitting, a BS&W bowl, a sight glass, and a sample valve. All of that in just 2 ports. So these modification kits can come in very handy. And equipment modifications is something that Deskcase offers on a complimentary basis to anybody that wants help modifying their equipment. We can help with the equipment modification plans. So just let us know. So the last thing that we really have to do in precision lubrication is verify. So now that we've selected the right oil, we have designed the contamination control process. We've modified the assets so that we can actually do those things. So we can change oil the right way. So we can control contamination and prevent contamination. Now we have to be able to verify that it actually worked. So oil sampling is a critical first step in oil analysis. Oil analysis, and this is a whole topic of its own, but oil analysis to me is something that is where the primary value is often overlooked, and that is that it is a proactive condition monitoring tool. So a lot of people use oil analysis to figure out when to change the oil, and that's fine. A lot of people use oil analysis to figure out if a machine is wearing badly, and that's also very useful. But what I really want to know from oil analysis is basically the things that we just talked about. Do I have the right oil in the machine? Is it healthy? And is it suitably free of contaminants? Is it suitably clean and suitably dry? So in that sense, oil analysis is a proactive condition monitoring tool that tells me basically tells me how well I'm lubricating the machine. And if I roll that up for all of my machines, I've got metrics there that tell me how well I'm lubricating my entire plant. So it's very, very useful and sometimes overlooked aspect of oil analysis. So oil sampling is the first step in oil analysis, and without good oil sampling, we're certainly not going to have good information on wear debris monitoring, probably not going to have very good information on contamination monitoring, at least particle counts. So we have options. We can use the traditional drop tube sampling method, which is cumbersome and difficult. We can install a sample valve, which makes it easy to get good oil samples, or if we're using a filter cart with that asset, we can actually circulate the oil and then filter or sample rather from the filter cart, which is probably a pretty cumbersome way to take an oil sample. But so first for drop tube sampling. Now, this is probably the hardest way to take a sample, and unfortunately, it's not a particularly good way to take a sample. This is the way that people sample when they're trying to get a good oil sample. But the main problem with drop tube sampling is that we don't know where the sample's coming from. You can't see inside the gearbox. So sometimes it's hard to even find the oil with a piece of flexible tubing that that probably came in a coil and has a kind of a screw-shaped set to it, so it's going to be challenging. If the asset is running, which is preferable when we take a sample, you could actually put the tubing into the moving parts. So it's really challenging to get a good sample, and it's almost impossible to get a consistent sample this way. But in general, if we must use drop tube sampling, if that's the best sampling method we've got, we want to try to make sure we sample as consistently as possible and try to get the sample extraction point at least 2 inches away from the bottom of the sump, from the sides, and certainly away from any rotating components. The best way to do this is to use what we sometimes people call a standoff method. So we can take some kind of rigid implement like a welding rod or a graphite rod or something, and actually fix the sample tubing to that rod. By doing this, we can insert that into the sump. The idea being that the standoff or the rod would actually touch the bottom of the sump, and then that way we would establish the height of sampling. So in general, we want to try to sample from about the midpoint in terms of depth in the reservoir, and we don't want to sample over in the corner of the sump or anything. We want to try to get in that live working zone where the oil is actually moving around. So that is one adaptation or modification of typical or traditional drop tube sampling that really kind of alleviates some of those problems. So the last thing that I want to leave you with is what to do with gearboxes when we store them. So if we have to shut down a gearbox for an extended period of time, or if we're caring for our spares, that are stored on a shelf in the warehouse. So the main thing we need to address is the fact that everything that's above the oil level inside the case is dry. It doesn't have lubricant that protects it from water, that protects it from other contaminants that might get into the system. So we need to prevent corrosion, because the two main issues here are the potential for corrosion of those exposed parts, and then we can also run into a problem called false Brinelling, where we can actually damage bearings that are sitting. It essentially creates a flat spot on the loaded bearing surfaces. So we need to address the corrosion, and we need to rotate shafts periodically to prevent this false Brinelling issue. So there's several ways we can address the corrosion. To address the false Brinelling, we simply need to rotate the shafts, probably at least once a month, while they're in storage or while they're sitting idle. As for corrosion, we could take the breather off, completely fill the case with oil, and put a plug in it. That's a lot of times that's a good recipe for leaks. So that's not always the best solution. We could install an additive called a vapor phase corrosion inhibitor. A lot of times this is used in stored parts, and it is something that we can add to the oil that will actually form a mist essentially inside the headspace that will coat everything with a preservative. Another way that people do this is by installing a desiccant breather, essentially the same way that we protect them while they're in service. So if we install a desiccant breather, even if the sump is not breathing, the silica gel is still in contact with the headspace inside the case, and it's going to maintain very dry conditions inside that case, probably down around 25% relative humidity. So the last thing that we need to do with stored components, if you have rubber seals, exposed seals on this thing, if it's going to be sitting for a while, it's a good idea to put a conditioner, a seal conditioner on those. Even grease works. Just wipe a little on there to prevent those from drying out. So protect against corrosion. Again, vapor phase inhibitor, desiccant breather, completely filled with oil, and then rotate the shafts periodically. Protect any exposed surfaces. Also a good idea to put a preservative on exposed shafts so that it's going to make it easy when it comes to installation. And again, rotate the seals at least once a month. So that is actually the end of our workshop for today. I believe we have time for some questions. So Olivia, do we have any questions from the audience?
Hey, Jared. Yeah, we do have a couple. So this first one is from an oil distributor. They have a prospect willing to do a test on a sample desiccant filter for a gearbox. Is it as simple as putting the breather on and waiting for it to change from blue to pink? Or should oil analysis be a part of this testing process to check for moisture and contamination throughout the test?
So if I understand the question correctly, is that you're asking if I install a desiccant breather, do I just presume that everything is good and not test it? So I would say you absolutely need to also do oil analysis. Now, in a very real way, a desiccant breather, at least with respect to moisture, a desiccant breather also serves as a type of condition monitor. This is especially true with the connected products. But if we see a rapid change in saturation, so if the breather, it's good for weeks and then all of a sudden it turns pink overnight, then that's telling us that there's another ingression problem. But humid air is not the only way that moisture gets into the sump. So oil analysis is a critical part of any contamination control measure. We want to use oil analysis to verify that we have the correct oil, that the oil's healthy, and that of course it's suitably free of particles and moisture. So I guess that's a really long way of saying yes, you should totally do oil analysis.
All right, so our next question is, where is the best place to install an oil sampling valve in a gearbox, an oil bath?
That's a great question. It really depends on, and I guess the answer is the easiest one. So when we do, we actually, me and some of my associates been for years doing modification plans for different assets, and it really depends on the make and model. So and what really matters is where the ports are. So, we want to get the sample extraction point in one of those live zones inside the system. So not in a stagnant part, not down on the bottom where there's, potentially years of information collected down there. So anywhere in a live zone, and like I said, a good rule of thumb is 2 inches away from everything. 2 inches off the bottom, 2 inches away from the sides, 2 inches away from moving parts. So beyond that, I would install the sample valve wherever it's easiest. Look at what ports are available. A lot of times we combine those, so we combine them with a sight glass, might combine them with a sight glass and a quick connect fitting on the same port. Sometimes we come in through the top and run a pitot tube, down into the sump. So it really depends on the particular asset. As long as we satisfy those, as long as we're getting the sample from a good location, then it's just a matter of picking the easiest sample installation point.
All right, thank you, Jared. So the next question is regarding shaft rotation. I've heard that there is a rule of thumb for shaft rotation by gearbox size, especially if there is a large inventory. Do you agree?
Not sure I understand the question. So are you saying that the rotation frequency should be based on the size of the gearbox? I'm not real sure. As to the correct frequency for rotating those shafts, I don't actually know what that should be. Off the top of my head, I know that most people do it somewhere in the neighborhood of 1 month to once a quarter. I'd probably go closer to 1 month, but I don't have any science to put behind that. So I'm sorry I can't give you a more specific question, but we have or rather a more specific answer to your question. But we do have that recorded, and we will be responding to all questions. So we'll get you a more detailed response on that, and also clarification on the question. Thank you.
Okay, so our next question is, we have a large number of gearboxes in small applications, less than 5 HP. What is your process to determine when to use oil analysis and contamination control that may cost more than what it's worth for the application?
Well, that's the question, isn't it? It's what's the cost, and that I think that's always the right approach. And what we have to decide is, what is the cost of a failure, and what is the cost of maintaining it? When you design a maintenance program, there are different maintenance strategies. You can use reactive maintenance, we can use preventive maintenance, we can use predictive or proactive maintenance, and the one of those that is correct is the one that's the most cost effective. So there's no real secret formula to that. It's pretty straightforward. What does that asset cost you when it fails? what is the cost of replacing it? What's the cost of repair? What is the potential impact on production? So what's the cost of any potential lost production associated with that? Now, if it costs more to extend the life of it than you do nothing. You let it run to failure. So there are certain things that we can always do that don't cost anything. We can filter all of our new oil. We can practice good storage and handling methods. We can install sight glasses on things so that we can do a routine inspection in a matter of seconds. So it costs almost nothing in order to do that activity. In terms of upgrading breathers, or obviously we're not going to put a vacuum dehydrator on a 5 horsepower gearbox to remove the moisture. That's, well, even if it was economically feasible, it's totally impractical. So, there's no real secret to that. It's just you can rationalize that though. With even just a little bit of data, you can sit down and add up the cost and add up the benefit and go with the best option.
All right, thank you, Jared. So the next question is, how often should you perform oil analysis on a gearbox?
Ideally, it would be once a month. A lot of times that's not seen as practical, and that kind of falls back to the last question, and there's no real straightforward answer to what is most cost effective. You actually got to look at it on an individual basis. A lot of times people have a budget for oil analysis, which is only going to allow them to do so much. So we can't sample everything. So I would say ideally once a month, at most once a quarter. If you get past once a quarter, your chances of catching something in time to really make a difference you really start to slide. I always, when I am teaching a class and I describe it as looking at your fuel gauge in your car once a week. It wouldn't that wouldn't be a very good method, because you'd probably run out of gas pretty often. Sometimes you'd catch it, but a lot of times you wouldn't. So we need to be looking often enough. So some of this has to do with the P to F curve. What is the P to F curve? And that P to F curve could be applied to other things other than a functional failure in the asset. It could be applied to water contamination. So let's just say that your oil gets badly contaminated with water. How long are you willing to let that go before you notice it? How soon do you want to know about it? And that's going to vary based on the type of asset and based on whatever it is that we're trying to measure with oil analysis. But for a quick answer, I'd say for critical applications, absolutely once a month, maximum once a quarter. If you're not going to do it once a quarter, I'd say don't bother.
Okay, and this is the last question that we're going to have time for. So this person said, you said 180 minutes to circulate oil was extreme. What do you recommend as enough time?
Well, that's asking a lot of questions that I can't answer very specifically. In general, you want to turn over the entire volume of that sump, at least about 6 times. Now, what that does is as you can probably imagine, with kidney loop filtration, it's not the same thing as taking the entire volume of the oil out and running it through a filter. That's what I would call an active filter pass. This, when we're using offline filtration, that's passive filtration. So it takes 6 times for that oil to be circulated to get the equivalence of a single pass through the filter, if that makes sense. So that's a minimum. But here's the thing, when you're filtering a gearbox, yes, it takes 6 passes, which is usually a few minutes, to filter the oil that's in the gearbox, but that's not really the problem. What you're really trying to do is clean the gearbox. So that, maybe it does take 3 hours. It is going to get cleaner and cleaner the more you filter it, because if this is a gearbox that is clean and you're just trying to keep it clean, then okay, the 6 passes, or a few minutes, however long it takes, that's going to be effective. If this is a gearbox that's been running without filtration for 3 years or longer, there's probably a whole lot of particle contamination that's in all the nooks and crannies. And when you implement periodic offline filtration, what we often see is a steady decline in the rebound particle count. So it's dirty, you filter it, it's clean, you come back 3 months later, it's dirty again. But it shouldn't be as dirty again. It should get less and less each time. So there's no great answer to that. Like I said, I think 3 hours is quite a bit, but I don't know for any particular gearbox exactly how long it should be. I would probably filter it at least 10 times. I'd want to turn that volume over at least 10 times.
All right, thank you so much, Jared, and thank you to everyone for joining us today. A recorded version of this webinar will be available to you shortly, and please make sure to join us next week for Connect to Your Assets, Condition Monitoring while Social Distancing. If you have not done so already, you can use the link that was just sent to your chat feature, or you can download the handout from the handout section of your GoToWebinar panel to sign up for these webinars. Thank you so much and have a wonderful day, everyone.